Okay, so the attendance is low, which is okay. We have finished all the unit, all the content in any way. So today what I'm going to do is open the session to you. So if you have got any questions that you want to ask, also for the whole syllabus, if you have got any topic that you didn't quite get it, be that as an example or a concept, anything. So if you do let me know, then either we have got 2 hours, one is today and one is on Thursday. So I'll try to address that during those sessions. If not, outside those, I could probably have make a small video or have some Zoom sessions in January. Have you received your exam timetable? Yeah. So the structures exam is on 19th of January, if I remember correctly. So 19th of January in the afternoon, 2 o'clock, for 2 hours is the structures exam. And that would be held in engineering building computer cluster. I think 1, 3 and 4, something like those. I don't remember. Yeah. Sorry, the computer cluster 3 and 4 are?
3, 4, and 5. Like 3 is in the first floor and 4 and 5 are in the second.
I don't remember actually whether 4 or 5 are upstairs, possibly. But we have to.
That's a good question. Are we allowed to bring empty notebooks in order to you all working out?
Yeah, I was going to say a few things about that. So, what you can bring and what not, I'll send you a detailed email possibly, because attendance is fairly low and in the class, so maybe it is better to convey that by email. And I have also get some information from the e-learning stroke IT services, that whether those computer cluster we can block access to emails and other things during that 2 hours or not, for example. So we'll look at that, but of course that would be invigilated during those period, those hours. So so that would be it would be like a normal paper-based exam. It would be. But these exams would be online, and question pattern would be very similar to what you have done so far. So you can assume you have done 4 tests, 30 minutes each. So it will be, if you put them all together, so it will be similar amount of effort that you need to put it in. Now, of course, in these tests, some are a little bit lengthy, some are a little bit less lengthy. But I have got some account from last year where we had for 2 hours. So I'll go by that, and student didn't complain about the time at all last year. So I'll use the same model from last year, and then we'll see how far it goes. So that would be again in January. I am going to, in Blackboard, in the revision folder, I'm going to probably make it available the past exam paper. Do look at those, but as you know, those are paper-based paper-based ones. So let me open that up for you. So you can see some of those questions as in past papers with the solutions given. So those are like another set of examples, if you could say. Now, be careful with the solutions, because sometimes the solutions are prepared and then are not, there may be some mistakes which are not picked up by the reviewers until one starts to mark. and then of course then these ones doesn't get updated. But what the main thing is, do look at the solutions and check the solutions for numerical calculations yourselves independently. But this can give you some idea about the exam, about the type of questions, but you would not expect anything similar in the terms of format in the online exam. As you have seen in the online exams, I ask only one questions, one aspect of a questions in one, except where you have to write a short answer, for example. There I could ask a number of things. So there will be definitely some short answer type questions in the final one. Multiple choice, different type, only one answer, more than one answer, and whenever there is more than one answer, there will be negative marking. So make sure that you, for those cases, you only answer that you are sure about. And that's it really. And I'll give you further instructions about the books that you can take or notes that you can take, etc. for the final exam. What I'm also planning to do, because the exam is on 19th, and most of you probably will go on to some form of vacations or break. And when you're back in January, I'll probably have 2 Zoom sessions where, because when you go through the material again, possibly you'll find that some of the things you don't understand and you want further clarification. So maybe before your exam starts, so the week starting, I don't know, maybe 10 till 17 in that week, I'll have a couple of Zoom sessions. So if you want to ask something, want to clarify something, do let me know during those Zoom sessions. And I'll probably keep it in the in the midday type of place, or one in the afternoon, so that you can join if you are in a different time zone things. So I'll think about that and put those couple of timings through emails. That's really it from me. Now, any topics that you want me to do today? Unless, yeah, go on.
I was a bit confused with the polygraph experience sheet.
Okay, I'll do that. You raised your hand? Yeah?
Yeah. I want to ask something. How can we find the second moment of area of any random shape?
A- any random say?
And
Yeah.
also for bending moment diagrams of non-straight beams. Because I'm looking at now.
Non-straight beam means you mean it's bent like a frame?
Yeah, I'm
Yeah.
taking a look at the exam paper.
Okay.
2019
Okay. Okay. Let me have a look at those two problems, those couple of problems. So, so first of all, Macaulay brackets for shear force. Yeah. Let me get a problem. Okay, so let me start a problem. This one I'll put it is in terms of the symbol so that you can change those. So let's say I've got a beam.
You haven't turned on the visualizer yet.
No, visualizer hasn't gone. Let's say you've got a beam like this, and which is support, 2 supports.
Not two supports. I mean, that's easy stuff. I mean,
one there?
No, I'm talking about a bent frame, the one that looks like that R looking letter Russian.
Yeah. Yours one is, I'm coming next. I'm going to do his problem first. So this is the macular brackets for shear force. So let's put some load. So let's put a concentrated load here. Let's put an UDL like this, and let's say the dimensions are as follows. This is say L1, this is say L2, L3 and L4, and let us also say this force is say F1, and that is a Q per unit length. And these reaction forces are, let's say, R1 and R2. Okay, is that fair enough problem for you? Okay. So we are going to do shear force for this using macular brackets. So we'll use the sign convention for shear force as follows. So positive shear force is like this. Left side going down and right side going up. So that's the positive shear force we'll be doing. So if we take x up to this distance, then we have got only R1 if x is in between this. And then that goes upward. So the shear force expression V would be R1 going up on the left hand side, so that is negative. So minus R1. And that would be for any values of x along the beam. So R1 would be there. That's just the shear force. And that's negative R1 because it is going, left side is going up rather than going down. Is that okay? Okay. Next is when we go beyond L1, then I'll get F1. And again remember the sign convention. So the sign convention is as follows. So positive sign convention for shear force is like this. So left side is going down for F1. So that means shear force is positive. So F1 is positive. But F1 is only valid for x greater than L1. Because if x is less than L1, F1 doesn't come in. Greater than x, L1. So we'll use macular brackets x minus L1. Now there is an issue here because this gives the shear force as force times the distance. Because if x is more than L1, then that would have some positive value there. So, but this is not the case. So what we need to do is, we need to put a power of 0 over that bracket. So that means whatever, so this part is 1 if it is positive. Now if x is less than L1, then of course that is 0. And if x is more than L1, then that is 1. So for x less than L1, this would be 0. And for x greater than L1, that would be 1. Okay? You raised your hand? Okay. 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 Now, if we go beyond L1 plus L2 in going up to here, then you have got some amount of UDL coming into picture. Now, the UDL is given as Q per unit length. So, if this distance is now x, the UDL is acting over a distance of x minus L1 plus L2. So L1 plus L2 over there, and the total distance is x. So the UDL is acting over x minus L1 plus L2. So over this, so this is the macular bracket, and that is time q. So that should go into the expression here. So plus q times x minus L1 plus L2. Now here we will not put power to the power 0 because we need here the value of x. That will give you the total load. So that will stay as it is, not power to the power 0. Because here it was the force already. Because this is shear force. F1 is already a force. And when the force is given as UDL, UDL intensity times some amount of length would give you the force. So that's why we don't put to the power 0. And then when it is beyond L1 plus L2 plus L3, R2 will come into the negative direction. So that would be minus R2, and distance is x minus L1 plus L2 plus L3, and this time of course it would be to the power of 0. So this is the shear force diagram using macular bracket.
What is that line above L1 and L2?
Oh, that is instead of, so this is nothing but that is combined together. Yeah, you could have put a bracket there as well. So it is x minus L1 minus L2 basically. So you could have put a, instead of that, you could put a little bracket there. Okay. Sorry? Because the load for uniformly distributed load is the load intensity times the length. So Q is not itself the load. So Q times the length will be make load. So we need this value here, if it is positive, to make it is the load or a force. Whereas F1 is already a force. If you put that, not put as to the power 0, this will be a moment, not a force. Whereas here, Q times the length is the load or the force. Is that okay for you? Yeah, okay. So if you then integrate, then of course it would be to the power. Now you don't integrate this shear force. So moment will come like this. So if you had a moment like this, for example, if you had moment m like this, for example, then in the moment expression you would get to the power of 0. Okay. So if you write down the moment expression for this case now, then how it will be? Now moment, we take positive as, this is positive moment. So the bending moment in this case would be R1 is going to create R1 times x, a negative moment according to this sign. So minus R1 times x. Now there is nothing moment will come until x is more than L1. So when it is more than L1, then F1 will create a moment in the positive sense, because on the left side it goes in this way, it rotates in this way, which is the same way as it's shown here. So it will create a hogging moment. F1 will create a hogging moment. So that would be, so plus F1 times x minus L1. Now this will not be to the power of 0 now, because this is a moment expression. We need force times the distance. So when x is more than L1, F1 times x minus L1 would be the moment. So that is not to the power of 0. But a moment, concentrated moment is acting at that point. So, and it is acting on the left hand side in the negative sense. So we put m times x minus L1 to the power 0, because otherwise we are multiplying moment with again a length. So if there is a concentrated moment, bending moment expressions comes with a Macaulay brackets to the power 0. Same way as the shear force, if there is a point load, that comes in the Macaulay bracket as 0. So the moment will come with a 0 sign now. And then Q is in here. So exactly, so that will create a clockwise moment. So Q times x minus L1 plus L2, that would be the load, times this square over 2, because that would be the distance. So that is the moment due to the UDL. Similarly, the R2 is the opposite direction, so minus R2 times x minus L1 plus L2 plus L3, not to the power 0 anymore, because we need to calculate the moment for this case. So this is the moment expression, and to the power 0 will come when there is a concentrated moment. Yeah, so now if you vary the x, for example, so put x equal to 0 to L1 value, then all these right hand side would be 0. So it will be minus R1 times x. So minus R1 times x means it will come in this way up to this point. So at the distance of L1, you will have this value as R1L. And then when it comes to x between L1 and L2, then R1x plus F1 times x minus L1. So it will the slope, so it will start to become less negative, right? So either it could go, depending on this value of R1 and F, either it can go this way or it can be less negative, let's put it that way. Okay, so depending on the relative value of this, so it can go along that, or along this. So anyway, it will be definitely less than that slope. And then again, if you put in the values of then m is greater than xl, so that bit is also negative, so you need to put in the values of m as well. So you go on and putting these values, and then treat those brackets as only give you positive. If there is positive value, then that is taken as the value, or if it is negative, then that's 0. So you can put in the Excel this expression with an if statement, for example, and then that's how to calculate it. Without the figure, without the values, it's difficult to draw it now, but that's a process. Yeah. Anything else?
So while using Macaulay bracket and considering distributed loads, sometimes the distributed load ends with a subtract.
Yeah. So with the Macaulay brackets, if the distributed load does not go till the end, then so if it in some beam, you have got a distributed load only up to a point like this. Then what you need to do is you need to convert, because when you write this distributed load expression, then that means x should continue till the end of the beam. So what you need to do is you need to convert this problem into this. So you need to convert this problem into as follows. So you put this uniformly distributed load continues till the end of the beam. So any distributed load which is not towards the end of the beam, you need to continue the other way around, and then of course this bit of the load is not there, so you start an upward load onto this bit. So you need to have these two expressions for those two cases. So if it is a triangular load, then what will happen? Okay. So if you have got a beam like this, and you have got a triangular load, let's say from here to here, then what you need to do is, again in this case, because the expression you will write, it will assume that the load is continued with the same slope or the same relative intensity in this case, like this, and then you subtract the bit of load that was not there. Okay. So that is how you deal with those loads. Just because the way we write macular brackets here with the uniformly distributed load, that x can be anything more than L1 plus L2, then that means that expression is valid due to Q. So if the load stopped before the end of the beam, then you need to take into account by this way. So you can say, okay, I'll assume my load continues till the end of the beam, then you could use Q times whatever x minus, etc. And then you put it another one which starts from that point to the end, so that the effect of these two are nullified. And same thing with the uniformly distributed triangular load. Is it okay? Okay. You can expect to write expression of shear force or bending moment using macular brackets in the final exam. So the way I'll be doing is possibly similar to the one that you have done in the last test. So not that problem, but something else problems in that way. Okay. Okay, so is this fine? Okay, let me get to, what did you say, a frame problem, right? Yeah, okay. So if I have got a frame, so let's say I have got a frame which looks something like this. Something like this. And you have got a load at the end of it. Let's say the load is something like this. Okay. So how to draw the bending moment, shear force, and so let's give a name to these parts A, B, and C, and let's say this load is F, and the distances are, this is L1 and this is L2. Let's say these are the distances. So one thing you need to note here is there are two members, AB and BC. And this is sort of a what is called, you can call a cantilever frame. Cantilever frame. Now you can draw the free body diagram and then start drawing the bending moment, shear force, axial force diagram in this case. Or as it is a cantilever, it's often easier to draw from the free end. So if the free end is C, then you can start drawing for the free end. So what is in the free end you have? You have got in the free end a length B to C and a force F. So I'm just drawing the free body diagram of part BC. So what would be its equilibrium? Free body diagram means we have to satisfy the equilibrium. So at that corner where I have cut from A to B, I would expect there would be a shear force going in that way to resist that force, and that should be the value of F. And this also creates a moment which both creates a clockwise moment in that sense, anti-clockwise moment. So that must be balanced by a moment at that point as F times L2. Then this whole thing is under equilibrium. So drawing the shear force, bending moment and axial force diagram next is easy. So if I draw it along this way, axial force. So the axial force is normally give it by N. So there is no axial force for this part. So that's 0. Axial force is 0 along this member. No force is acting along the length. So what about the shear force? Now shear force, you can see, is going along this way. So for F and continuous along this part. So this is F. So this is shear force. Now whether that is positive or negative depends on whether you look this part in this way or that way. It depends. Now you could say, you could choose either, and you could say, okay, my shear force is positive in this case. I'll take as this shear force as positive, for example. This is positive shear force diagram. So if you do that, that's positive in this case. So you can choose which way when it comes to the frame. What about bending moment? Now bending moment, there is a choice that people make, especially it comes from the industry, that what they use bending moment is draw on the tension side of the beam. What do you mean by the tension side? Now imagine this is the part BC and you are putting a force F at one end. So it is like this, F at one end is like this. So if you put a force in this part of the frame, it bends in this way, right? So if I am holding, so you said this is the part BC, I am holding it. So my finger is point B. My finger is point B. And I am putting a load F in that direction. How does it bend? It bends in that way. So if you consider detailed view of it, so this side, left hand side will have the tension and the right hand side will have compression if it bends in this way. So the right side, the fibers will come closer, and the left side, the fiber will extend. So the tension, if it bends this way, tension is on the left hand side and compression is on the right hand side. So the industry standard is to draw the bending moment on the tension side. So, and if you see the beam problem that we have done, I have chosen the sign convention for the beams. So this sign convention for the beams will match exactly. So my sign convention for this one would definitely show you that the positive moment is drawn on the positive side. So on the tension side in this case. So draw bending moment also, left hand side is the tension. So as you go up, your F times, so how the bending moment should be featuring in? So if you go up, your bending moment will increase. So F times X until it becomes F times L2 at that point. So tension side is in this direction. So I'll put that as a straight line and going that as F times L2 at that point. So F times X is equal to F times L2. So that is just drawing on the tension side. So that is nothing positive or negative we say when it comes to the frame, because which side is up or which side is down. You may say, okay, I'll put it in this way. Now what happened if the frame was something like this? This is the frame. Then if you say, okay, this beam, that way positive, what about that one? That could be, are you saying this way positive or that way positive? Outside positive, inside positive. And then if you have got another story, then what happens to this one or that one? So in industry and lot many software, they use bending moment, draw that for a frame on the tension side. And the sign convention I have chosen, it will automatically satisfy the tension side for the beam, because our sign convention is, this is the sign convention for bending moment. Okay, so this is the positive sign convention for bending moment. Now if you have got a simply supported beam under a point load, the bending moment according to our sign convention is like this. So we are already drawing on the tension side. So bottom side will be under tension. So that's what we are drawing. So this sign convention that we have chosen will automatically satisfy the tension side problem that we are doing over here. So that completes for B to C. What about part A to B? Now let's draw part A to B here. So part A to B. Now at joint B, this was the case. You had FL2. So for joint B, for part AB, the reaction would be equal and opposite. Why? Why, you might ask. So let me draw that thing over here with a little bit of diagram over here. Say I am drawing this part again. So I am drawing this part again. So you have got part B to C. So this is point C, that is point B, and I have got force going through. So this is force F, and then I have got shear force going in this direction as F, and I have got a moment which is acting here as F times L2. Now this is connected with the joint in here. So let's say this joint is something like this. So this is the joint B, for example. Okay, and then that is connected with part A to B over here. So I've taken a joint, I've just separated out the joint in there. So you know, according to the third law, that's action and reaction. So if F is going at the end of this vertical member going right to left, then on the joint it should go in the opposite direction, because these should be matching equal and opposite at the end of the joint. So this should be F, for example, here, and then this should be also in the opposite direction, so that would be F times L2. What about the other end? This is not in balance, so this should be F, and that is would be the other way around, F times L2, so that this is balanced. Now what about the end of the horizontal member? So you would expect F in this direction, and FL2 is under that direction. Is that okay? So for completeness sake, it would be, for this we do the equilibrium of this part, it would be F in this side, and this F carries on as an axial force. Just one second. So there is no other moment but to carry this is as FL2. Go on.
Shouldn't the moment on the right side be transferred? Because in this case, both moments are the same direction.
Yeah, because over this joint, so what I've done is I have cut in here, for example.
I meant at end B of green maybe.
Here,
Okay.
here.
Yeah, there the moment should be the other
Oh,
way.
yeah. Thank you. So this is what? Clockwise. Thank you so much. Thank you.
Wait, how? Wasn't it already clockwise beforehand? Oh, right. Yeah, sorry.
Yeah. So this is clockwise. This is anti-clockwise. So this is clockwise. This is anti-clockwise. This is clockwise. That is anti-clockwise, and that is clockwise. And it also makes sense that if F is there, that will create an anti-clockwise moment. So that must be balanced by a clockwise moment. So this is the free body diagram of part AB. So part AB free body diagram is F, and you have got a moment which is F times L2, and in this case F times L2. So we can draw the shear force axial force diagram now. So the axial force diagram would be, so axial force is in tension. So the tension normally we say positive. So this is tension, or you could say tension, because F is extending that. What about shear force? Now there is no shear force because there is no force which is acting perpendicular to the axis. So the shear force is 0. What about moment? Bending moment. Now bending moment is in this direction. Now this is, as you see, this would bend in that way. This is a sagging moment. According to our sign convention, this is negative, and if we draw on the tension side, this would be negative anyway, but it is also constant. So if you try with FL2, then no load in between, so it's a constant bending moment under it. So drawn on the tension side, so this is bending moment. Okay? So that completes the shear force, axial force, and bending moment diagram for this case.
I know I'm basically just wanting to ask for the solution of question 5 because I'm confused by how it looks. But if the cantilever thing was standing on its cantilever root, would the same thing?
Exactly the similar thing. Now, of course, if the load here is downward, then that would have axial force and no shear force, and no bending moment in this part.
Yeah. However.
Yeah, but here it will have shear force and bending moment.
Okay, so the bending moment diagram for a cantilever frame, shaped like that must are bend.
Yeah.
With a force acting on that bend.
Yeah, if you join these two, so sometimes people do it as a jointed one. So if I draw the whole frame, then how does the bending moment diagram would look like? So the bending moment diagram would go like something like this, and then so that is F times L2, and then F times L2 over there. So this is bending moment diagram for the whole frame, like that.
That's the bending. Wait, so if we were given a bending moment question in an exam, that's how it would look like?
So that is if you say bending moment diagram for the whole structure,
Yeah.
whereas here I have drawn them by two parts. Yeah.
Yeah.
Is that your question?
Yeah.
Okay.
Should we draw them as separate parts or one whole diagram?
It depends on the question, but mostly if you do either way, that's fine. Either way is fine. Now, normally you should get into the habit of drawing as a complete one, because that way it is much more complete in that sense, so that you can see the whole frame and draw the bending moment diagram. Yeah. But to start with, better to separate it out so that it increases your understanding and then join them together. But once you get proficient with equilibrium and free body diagram, you don't even need to go through all this step. You can draw completely from start. You could say, okay, I have got this frame and I have got a load. So I'll start drawing this in this way. Which way it is going? It is going putting the, so as I go up, my moment is going to increase linearly, and you will say, okay, so it will be a linear curve like that. And which side I draw, this side or that side? Now this should bend in this way, so I'll draw it in this direction. And when I am at this point, the moment is maximum F times L2. Now if I start getting into this side, the moment does not change, because moment at this location is F times L2. Moment at this location is also F times L2. If I go along this length, my moment value doesn't change, because the length or the lever arm for the moment is the same. So the moment will be constant along that path. So that's how you will draw when you get proficient with the idea of the free body and equilibrium. Any other topic? Yeah.
I had a doubt regarding deflection. So while assuming the deflection, it was mentioned that we assume that there are no axial forces. So if there were axial forces, how would it affect the deflection?
Yeah, if there is axial force, then of course the deflection should be affected. But this is what is called a second order effect, and that you will learn in second year with when you do buckling and tension structures, for example. So the equations that we have done is, if you remember, bending equation is EI d2y dx2 is bending moment, right? Now if you do it two more differential equation, because you know dm dx is equal to v. So if you differentiate it again, you will get EI d3y dx3 is equal to v. You also know that dv dx is equal to load. So if you differentiate it again, EI d4y dx to the power 4 is equal to load. Now if you have got the axial load into it, then n times dy dx would be added into this load. So if n is the axial load and dy dx is the slope of that load. Okay? So then it's a complicated differential equation, it's a fourth order differential equations, and you need to solve that. But that would be essential when you do cases like buckling. Okay, so that would be n times d2y dx2, etc. would be your load. Any other comment? No? Yeah, so that's why people, for a frame, they draw on the tension side, and then they get rid of the concept of whether it is positive or negative. So they will draw the diagram on the positives, on the tension side of the beam. So you don't need to see whether that is positive or negative, whether it is up or down. You don't need to see, because there is a problem with on the vertical cases, for example, which side is positive, left positive or the right positive. So they don't do that. So in the industry, so whether they say that whether my bending moment, I'll see whether that is bending the beam this way, frame that way, or that way. If it is bending in that way, this side is tension, because this side fiber would be extended. So I'll draw the bending moment on that side. It has also got advantages because some materials are weak in tension. For example, concrete. Concrete has got very low tensile strength. So how do you use concrete? You put reinforcement, which will take tension. So it is then easy for a contractor on the ground to see which side of the cross section your reinforcement should go by looking at the bending moment diagram. That in this case, if it was a concrete frame, then you'll put, okay, more reinforcement on the left-hand side, because that's where the bending moments are. That's the tension side. And the reinforcement is taking the tension. Okay, so please do let me know what are the things that you'd like me to cover, and you can do that later as well. Tomorrow I'll release the marks for the 4th quiz, and we'll keep in touch definitely through discussion board and Zoom link as well, so that you are prepared for the final exam. Okay, and the deadline for the group coursework is today. Some of you have asked me about the extension. I really don't want to give any extension because the date has been fixed, and also I don't want you to spend awfully long time on this piece of coursework. Whatever you have done until 11:30 this evening, submit, and one person for the group can submit it all. And if your group people did not put in effort uniformly, so then put in a peer assessment form. Okay, you raised your hand. You will come over here. Okay, thank you. Thank you. See you on Thursday.
Thank you very much.
Thank you.
For the group work, we had done few calculations, but we could not include in the main file. Could we add it as an appendix?
No, everything is in there.
I mean, we could provide a link and...
No, 2 pages.
So could we use 2 A3s?
No, 2 A4 or A3. What you could do is, some people got rid of that was by putting a video. So they make PowerPoint slides and then make video of that.
So we can't submit a video and A3?
No,
Anyone?
anyone. Okay.
Well, when calculating the second moment of area of a cylinder
Yeah.
using triple integration, we can do it in reference to the
Oh,
XY
second
plane.
moment of area is just for a flat surface, for an area. Second moment of area is not for a solid.
No?
No, because that you're talking about radius of
Moment
gyration.
inertia.
That is in the mechanics. That's for the whole 3D body. But in this case, it's a plane section.
Can't we though?
You
What
can
if,
do it for a circular cross section.
but we can't use this to calculate the second moment of area.
Second moment of area is different to the moment of inertia. Second moment of area is primarily for a flat axis, flat area, two-dimensional area.
So in 3D, we cannot assume that.
3D is not useful here. 3D, what will come here is something when it comes to the moment of inertia primarily. That is a different concept into this case. So there it has got a definite mass. So you can use the same principle to calculate the moment of inertia, which will be used in the mechanics next semester. But in this case, we'll assume it's a flat section.